All right, here we are with part three of our four-part integral lecture. And today we're going to be talking about so actually kind of the nitty-gritty of integrals and getting into the actual rules. So things like the power rule or the exponential rule, the logarithmic rule, things like that. We'll also talk about integral properties that I've kind of alluded to a little bit, but we'll actually see them formally now for the first time. So I will be honest, these formulas will take some time to get used to. As I've said before, and I'll say it again, just doing problems, just doing these, just do examples, just find practice problems and work them out. That's your best way of just getting comfortable with these and how they work. So with that being said, let's go ahead and get into this. We're going to look at the power rule. This is for integrals. So this actually, while it does not look like it, it says the same thing as the power rule for derivatives. It doesn't really look like it at all, but it really does mean the same thing. Let's kind of dissect this. So if I'm taking an integral of a polynomial, so like x squared or x cubed, something like that, then what I do is I add one to the exponent. Notice that when we took a derivative, we subtracted one. So there's kind of an opposite going on there, where instead I'm adding one. And then you'll notice on the derivative, I actually multiplied, which we always verbally said is, hey, let's drop this down. But it's really that I'm multiplying by an n. Well, here I'm dividing by that exponent, which is now n plus 1. So let's go ahead and look at this in an example. So if I have the integral of x cubed dx, just using this formula, what I'm going to do is I am going to add 1 to that numerator right there, or excuse me, to the exponent, and then that's going to result in a 4, right? 3 plus 1, which means that I just divide by 4, which I'll just write as 3 plus 1. So it's x to the fourth over 4. You might write that as 1/4 x to the fourth. And let's not forget, I almost forgot it here, but I didn't, plus c every time. Gotta have that. Don't just wait and write plus c at the end. You gotta have it all the way through because otherwise your equality signs aren't correct. So we're seeing that example right there with x cubed. It really works out the same way with with others like this. I mean, I could have x to the 83, and what I'm going to do is I'm going to add 1 to that and then divide by whatever that was, plus c. I personally like to write this as 1 over 84, x to the 84, instead of this way, but it doesn't really make a difference either way. And there you go. I mean, that's the power rule. Basically, it's just saying, hey, if you have a polynomial and you're taking an integral of it, add 1 to the exponent and then divide by whatever exponent you just got now, your new exponent, then add c. And so that's your power rule. I will make a note here that n cannot be -1. The reason for that is because if n is -1, this right here is 0, and that's bad. We don't want to divide by 0, right? That's something that we never want to do. So n cannot be -1. We'll actually get to that case towards the end of this lecture. So we will cover that, but the power rule works for n not equal to -1. Let's do an example here, and I'll erase this top example here just to keep it all on the same page so that we can see this formula. Actually, want to do this with let's do 1 over x cubed right here. Well, what we can do, and we've done this same thing with derivatives, is before taking the integral here, we can rewrite the function as x to the -3. And now the power rule just still applies. I can now add 1 to that exponent and then divide by the resulting exponent. So I just have, and let's not forget plus c. So now I have x to the -2 over -2 plus c. And rewriting this, I might just write -1 over 2x squared plus c. So I'm dropping this negative exponent down to the bottom. This negative sign right here, I'm just writing it right out front. And then the 2 is still on that denominator. It's down on the bottom there. So there we go. We've got -1 over 2x squared plus c. That's an example when you have a negative exponent, something that doesn't explicitly look, yeah, this actually isn't a polynomial, so maybe I shouldn't use that word polynomial to describe this, but if you have something that looks like x to the n here, then this power rule is how you'll do it. And there we go. So we got the power rule there. N can't be -1. We'll get into that example later. Let's move on to the exponential rule here. And really what I really want you to focus on is this right here. And I'm actually going to box this again, just to make that very clear. This right here is really the, well, and actually let me do this. So we'll have all these formulas here, but this right here is really the nitty gritty. That's the part that I really want you to focus on. Honestly, you shouldn't even need these at all if you have this right here. These other three just are not even necessary. They're helpful, but they're not necessary. If you can, memorize all of these, that's fine. I highly recommend not being dependent on memorizing them, though. It's very easy to forget things that are memorized on an exam, and this is really the way to go. So, with all that being said, let me get into this. We've seen before that if I take an integral of e to the x, I just get e to the x. Same thing with the derivative. If I take a derivative of e to the x, I just get e to the x. So this is a really simple formula. It's just e to the x right there, boom. And then I got my plus c. This right here, as I've said, this is really the big formula. And this is just an exponential integral, but it's just more general than e. And so we've seen several examples of this already. If I have a to the x, I again have my a right there to the x, but then I have to divide by that ln of a right there. And we've seen that example before several times. And so this is just our simple exponential rule right there. I'll go ahead and write that. This is our exponential rule. So you'll notice that it's similar to the derivative exponential rule. On the derivative exponential rule, we actually multiplied by an ln of a. Here, we're dividing by an ln of a. So kind of a little opposite game going on there. So coming back here, why do I even give this to us? As I've said over and over, this is really the only one we need, this top right box. So why do I even give this to you? Well, if a is equal to e, then this is ln of e, which is just 1. So it simplifies down really nicely. So I box this and I write it and I sort of give it to you as a formula just because it's just a specific case of this right here, but it's a case that pops up quite often, and so it's worth sort of noting. It's worth just knowing that. If you gave me a list of integrals to do, and e to the x was there, I'm not going to bother showing this work. I'm not going to write e to the x divided by ln of e equals e to the x over 1 equals e to the x. I'm not going to write out all that. I'm just going to say, hey, it's e to the x, because I've just done them quite often, and I'm comfortable with that. So, and you're welcome to do that too once you get comfortable there. So I just write this down just because it pops up a lot. It's just a specific case of this, though. That's why I say you don't even really need that right there. And the same goes for these right here. We're gonna get into this idea of substitution of integrals in later lectures, and so I'm sort of hinting at that here. But for now, just by inspection, we've seen these before, where if I have like e to the kx, so k is just a constant. If I have like e to the 7x, then we have to do that 1/7 out front. We have to divide by that constant k, and we've seen several examples of that already. So this is my formula here. Again, it's pretty much just this, or excuse me, this guy right here in the bottom left is pretty much just the top left, but it just has this extra facet of, hey, there's like a k in there, and it changes things a little bit. It's kind of like, hey, maybe there's some chain rule going on there, and that's what I'm alluding to as substitution. So with this right here, the reason I'd say that you don't really need to memorize this is because you're going to get we're going to learn later about substitution, and you're gonna be able to do this problem with this idea of substitution. For now, though, I mean, it's good to just know, hey, if I have something that looks like that, I do have to do this sort of division by k right there, and then obviously plus c. So there we go. There's our exponential with a base e and a constant mixed into the exponent there. But just as we saw before, I don't have to have e as my base. I could have a. So the only thing that changes is, well, just like here we had division by ln of e, we also have division by ln of e here. Well, now we have an ln of a on the bottom as well. So it still looks almost identical to that right there, but now there's just this extra ln of a thrown in there. And again, you don't necessarily need to memorize this because we're going to learn substitution in a little bit, and that's how we'll tend to do this problem. So I'd really focus on this. This is what you really have to memorize. This is going to just save you a lot of time to memorize. These, you'll probably just do them often enough that you just recognize that that's what it is. Slash, you'll do substitution and you won't even think about these formulas. But these are all here for you on this slide, in case you want them. So exponential rule right there, that's the big guy. So let's go ahead and move on to logarithms. And here we're going to see this 1 over x. And actually, remember, this is the power rule. Or excuse me, this is something that you might try to use the power rule on. You'd say, hey, this is integral of x to the -1. That looks like an x to the n. So let's do power rule. But power rule doesn't allow us to, or we're not allowed to use the power rule here because this is a -1. And remember, like we said, power rule, we can't have n equal to -1. So when n is equal to -1, it actually turns out, and we've seen this before, but you get ln of x here. And checking it, you could take a derivative of ln of x and you get 1 over x. So that's good. This works out. We have our plus c. The other thing I want to mention here is this absolute value. That is actually critical. It's really important that you put your absolute value there. There will be cases that we'll see where the absolute value isn't necessary, but I would write it in there. So just sort of a prelude to that, you may end up doing an integral of stuff, which I'm not going to bother explaining what that stuff would be, dx, and maybe you get an answer of like ln of absolute value of x squared plus 1 plus c. Well, really what I'm getting at here is that this x squared plus 1, this is already positive. And so there's no point in sort of putting in absolute values surrounding that. You could just write parentheses, but it's not wrong to write absolute values. So I just always emphasize, put the absolute value there, put the absolute value there, put the absolute value there. Just always put it in. You're never going to be wrong having it, but you could be wrong if you just write parentheses instead. So put the absolute value there. Integral of 1 over x is ln of x. That's logarithms right there. What I actually don't have a slide for right here is similarly what it might look like for a not a natural log, but an log log. So just like a log base 10 of x, or like a log base 3 of x. And the reason I don't have a slide for this is because we're actually going backwards here. So remember, we had multiple sort of formulas for how to take a derivative of ln of x, or log base 10 of x, or log base 3 of x. Like we talked about how to do derivatives that. But here we're doing integrals of something that looks like an x to the n, and we're getting a logarithm out. And when you do that, it turns out that you only get this natural log, ln of x, which is log base e. There's not really a way to get these guys out as your answer from an integral. And so this is just all we have. We have that ln of x, not a log base 10 of x or a log base 3 of x. Just to be clear as well, we're not going to deal, well, yet at least, we're not going to deal for quite a while like looking at an integral of ln of x dx. That's just something that I just wouldn't expect you to be able to do because you haven't learned the methods for doing that. Likewise, you're not going to see something like log base 10 of x dx or anything like that. So nothing necessary for LOGs here, we'll just have ln there. So that's good. So that's logarithms right there. That's our formula there. Obviously, there will be more complicated problems than just this. Nice simple 1 over x, but we'll deal with those as they come. So now we've seen these integral formulas, and just to recap, we've got. Let's go ahead and do a new slide here. So we have the power rule, which says that the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. Change the color here. Come on. Color change, red. There we go. And then we have the exponential rule, which states that the integral of a to the x dx is going to be a to the x divided by ln of a. Remember, with derivatives, it was multiplied by ln of a, but here it's kind of the opposite. And then the logarithmic rule, which is pretty specific. Absolute value of x right there, boom, plus c. So these are our 3 big rules. Obviously, there are variants of the exponential rule, and the logs can get a little bit more complicated, but for now, that's just kind of what we're going to leave it at. So let's move on now to integral properties. So these should be pretty easy. We've done these with derivatives. Let's go ahead and look at them. So the constant property, it just says that if I have a constant in my integral, I can pull it out front and I can just kind of forget about it. And I can do this integral and then just multiply it by that constant. So a great example of this would be if I gave us the integral of 3x to the 4th. Well, what I could do is I could just kind of bring the 3 out, almost just like forget about it, do my integral of x to the 4th, and then I'm good. And let's actually do this. That integral of x to the 4th is me adding 1 to the exponent, and then, so I get 5, and then I divide by that 5, which I'm writing in the form of multiplying by 1/5. Same thing there. And I add c. Well, when I do this, what you'll notice here is that I end up with 3/5 x to the 5th plus 3c, because I'm factoring that in, that sort of, well, I'm distributing this 3 into both. Now, what I'm going to do here will probably look very fishy. It might not seem allowable or legal, but it is. I'm just going to write c. And really what I'm doing here is I'm saying, all right, this c that we put in here, oh, sorry, I erased. This c that we put in here, it just stood for any number that you can think of. It's a placeholder for literally any number in the world. So when I multiply it by 3, all that does is it just gives me any number in the world. And it doesn't really make a difference if I write c or if I write 3c. It's still just a sort of a blanket representation for any possible number that there could be out there. So rather than writing 3c, I just simplify it and just say, hey, let's put plus c. It's still just standing for whatever number you can possibly think of. It doesn't really matter, nor does it really make sense to bother writing a 3c, because it's just saying, hey, if I take any number you can think of and I multiply it by 3, well, you're just going to have another number. And so there you go. You can just kind of replace it with a c. What some people like to do is they like to write hey, let's set 3c equal to d. And then d is this new variable, new constant. And then they'll just say, well, hey, then instead of writing d, I'm just going to say, hey, d is equal to c. And that's kind of how they can convince themselves to work around this, that, I just kind of get rid of the 3. But I just like thinking about it that 3c is just, it really just, it's a placeholder just for any number you can think of. So there's no need for the 3, just write c. So there we go. That's an example of the constant property where I've taken this 3 right here and I've brought it out front and then just done the rest of my integral and then multiplied back in. So there we go. Constant property right there. We will use that over and over. And let's look at the sum and difference property. And what I probably should have written here, parentheses around that. And actually, instead of parentheses, what you might see occasionally is you might see brackets written here. They mean the same thing as parentheses in this case, but they just maybe look a little nicer than parentheses, just kind of trying not to have this effect of just like multiple parentheses, stacking on top of each other. So put that there. And then basically this just says the same thing that it said for derivatives. If I'm adding or subtracting two functions together and I'm taking an integral of that, I can just do each integral separately. So maybe I give us something like the integral of 2x plus e to the x dx. Well, I'm just going to split this up. I'm just going to do the integral of 2x, and I'm going to add to that just whatever the integral of e to the x is. When we do this, we get x squared, as we've seen. Let's add a plus c there as well. And then we'll have just e to the x plus c. And again, we're seeing the same thing where, well, if I add these c's together, do I get a 2c? Well, let's just not bother, and let's just go ahead and write c, because it's just simpler, and it's just, there's no point in really writing 2c. We could just write c. Also, you might even say to yourself, well, wait, how do I know these c's are even the same? They don't have to be the same. Maybe I write c1 and c2, right? So if I do that, then I could say, hey, I've got my x squared plus c1 plus e to the x plus c2. Well, I'm just going to say that that's x squared plus e to the x plus just c. And maybe I sort of put off to the side, hey, this variable c, this constant c, I'm sort of redefining it as c1 plus c2. And there you go. Now we're sort of resolved in this, this tension of like, why do I have multiple c's here? So either way you want to think about it is fine. Really what you'll probably do is you'll probably just do your integral and then just add a c on the very end of it. But I just like to show explicitly sort of why we get there and how we get there. And that, yes, it is a little bit, fishy just going from here to there or here to there. So that's that. Plus c's are weird, but we'll make sure that we deal with them appropriately. So sum of difference property and the constant property. Honestly, you'll probably just do enough integrals that you won't even think about using these properties, just like derivatives. You probably you're not going to be sitting there in your head thinking, oh, I have to use the constant property. You're probably just going to do it. And after you've seen enough examples, you won't even really think twice about it. So there we go. We've got some properties and we've got some formulas here. Keep these ingrained in the back of your head. We're going to be using them over and over and over. And that'll be the third part of our 4-part lecture on integrals, and we'll call it there.